Exam corrections. Apologize for the crumpled paper. It got squished in my backpack. So here we have an exothermic reaction taking place in an adiabatic batch reactor. Temperature does increase because, as an exothermic reaction does release heat. So a temperature increases. Conversion of the reactions also increases because the reactants are being consumed and products are forming. So naturally the conversion is increasing. With time, equilibrium conversion does decrease due to Le Chatelier's principle, and an exothermic reaction as temperature increases, that will force the equilibrium to shift to the left, which is the side of the reactants. So the equilibrium conversion decreases, and the rate constant in the forward and direction and in the reverse direction both increase because as temperature increases, they increase due to the Arrhenius equations. They are directly proportional, which is the same for the forward and the reverse direction rate constant. For part B, we have assuming this reaction behaves elementary. I did have the correct elementary reaction the first time around. What I got wrong was RB. The relationship between RB and R is RB is equal to negative 2R because there's 2 moles of B and B's in the reactant, so that's where the negative comes. As for C, there's only 1 mole of C and it's in the products, and that's why it's positive, so RC is equal to R. Problem 2, we have a Levenschild plot and A goes to B as conversion goes from 0.3 to 0.7. The concentration of A decreases because A is being consumed and forming B, and that's why the conversion is increasing. So the concentration of A, of course, decreases, and the reaction rate as shown above increases because, and that's looking from the plot, you can see from 0.3 to 0.7, 1 over RA is decreasing. That means RA is increasing, indicating that this range has negative order kinetics. We know that normal order kinetics, the concentration increases as the reaction rate increases. But for negative order kinetics, concentration decreases, the reaction rate increases. Therefore, mixing in this range tends to increase the reaction rate. Why does mixing in this range increase the reaction rate? Because in a CSTR, negative order kinetics is better. And mixing would decrease concentration. And when mixing decreases the concentration, negative order kinetics, the reaction rate increases. So we want mixing, and mixing increases the reaction rate because of that. The key difference between a CSTR and PFR. CSTR, a continuously stirring reactor, which is better for negative order reactions, and in the Levenschild plot is described by a box. While the PFR is thin slices made up of small batch reactors, and it's also the area under the curve in the Levenschild plots. For part B, I said case 2, PFR, then a CSTR, and I initially got that correct. For 2C, since we already established that PFR comes first, we do a mole balance on the PFR, and we know the relationship of FA is equal to FA naught 1 minus XA. So from that, we derive that dFA becomes negative FA dXA. FA naught is constant, so we can pull that out of the integral, and then we just isolate the volume by dividing R over, and the dXA over R is the area under the curve. So area under the curve, you can see it is actually a rectangle and then a triangle from 0 to 0.3. So we do area of rectangle, area of triangle, add them, multiply them by FA naught, and then we get 90 liters for CSTR. We also have the mole balance for CSTR. We have FA naught 1 minus XA in minus FA naught 1 minus XA out, described by the relationship I previously mentioned from FA and FA naught, and that is because coming into the CSTR, as we can see here, is a conversion of 0.3, and leaving the CSTR is a conversion of 0.7 in case 2, which is why we have X in and X out. Rearranging that to solve for V and multiplying that by the rate, we get 60 liters. The reaction rate, we get 60 liters. For problem C, for problem 3, I got this all correct except for the final answer. So we solve for delta G, plug that into the Ka naught equation, solve for delta HF, the heat of formation, and then we do a spicy table to find our Y mole gas fractions, and we use that to find Ky, relationship between Ky and Ka. We know that overall stoichiometry is 0, so Ky is equals to Ka. And then in this temperature equation, we use the heat of formation and Ka. So of temperatures through algebraic manipulation, we get 523 Kelvin. and properly inputting the calculator, which wasn't done before. For question 3b, we write elementary form of the rate limiting step. And step 1 is in quasi-equilibrium, so the right elementary form for that as well. We want to isolate the catalyst sites, so we solve for the concentration of O catalyst, and then we form a site balance. So C star total is equals to concentration of the catalyst plus concentration of the O catalyst, so that we can have, so we can plug these new forms back into the rate limiting step. And we can get rid of all of the catalyst sites and have it all in terms of C total or other concentrations. And then through algebraic manipulations and simplifications, we have our final form. And for the extra credit, for problem 2, the most volume efficient way to run the reaction was to use a PFR up to converge, volume efficient way is to use PFR as a conversion of 0.1, then a CSTR. And this is because, as you can see in the Levenschwiel plot here, from 0 to 0.1, if a PFR is used, that's just on area in the curve. But if CSTR is used, it would be much bigger than a PFR. So it would not be minimizing the volume. That's why a PFR is better until 0.1. Then a CSTR up to conversion of 0.7. The total reactor volume in this would be 102.5 because now we would plug in 0.1 where we had initially plugged in 0.3. In the calculator, getting us to 102.5 as the new total volume.